The idea of the atom is surprisingly old. Around the 5th century BC, ancient Greek philosophers Leucippus and Democritus first proposed that matter was made up of tiny indivisible particles called atomos, meaning uncuttable. They believed that atoms were eternal, infinite in number, and constantly in motion. These early atomists imagined different shapes and sizes of atoms, explaining the diversity of substances we see in the world. Liquids, for example, were thought to be made of smooth, slippery atoms, while solids were composed of rough, interlocking ones. While remarkably prescient in some ways, ancient atomism lacked empirical evidence. It was more of a philosophical concept than a scientific theory. The idea of atoms faded into the background for centuries, overshadowed by other theories of matter. However, the seeds of atomism had been sown. The concept of a fundamental, indivisible unit of matter would resurface centuries later, paving the way for modern chemistry and physics. In the early 19th century, an English chemist named John Dalton resurrected the atomic theory. Unlike the Greeks, Dalton's ideas were grounded in experimental observations, particularly the laws of chemical combination. Dalton proposed that each element was composed of a unique type of atom, all with identical properties. He further postulated that atoms of different elements could combine in simple whole number ratios to form compounds. This explained why water always had a fixed ratio of hydrogen to oxygen 2:1. Dalton's atomic theory revolutionized chemistry, providing a framework for understanding the composition of matter and the nature of chemical reactions. His model of the atom was simple, picturing it as a solid, indivisible sphere. While later discoveries would prove this model to be incomplete, Dalton's work laid the foundation for the modern atomic theory. His emphasis on experimental evidence and quantitative analysis marked a turning point in our understanding of the atom, ushering in a new era of scientific inquiry. Toward the end of the 19th century, the indivisibility of the atom, a cornerstone of Dalton's theory, was challenged. In 1897, J.J. Thomson, a British physicist, conducted experiments with cathode rays, mysterious rays emitted from electrodes in a vacuum tube. Thomson discovered that these rays were not rays at all, but streams of negatively charged particles, much smaller than atoms. He called these particles corpuscles, later renamed electrons. Their discovery shattered the notion of the atom as a solid, indivisible sphere. The atom, it seemed, was composed of even smaller particles. Thomson proposed a new model, the plum pudding model, in which negatively charged electrons were embedded in a positively charged pudding, like plums scattered throughout a dessert. This model, while inaccurate, was a crucial step toward understanding the internal structure of the atom. The discovery of the electron marked the dawn of subatomic physics, revealing a hidden layer of complexity within the atom. The quest to understand this subatomic world would lead to even more profound discoveries in the decades to come. In 1911, Ernest Rutherford, a New Zealand-born physicist, devised an experiment that would forever change our understanding of the atom. He bombarded a thin gold foil with alpha particles, positively charged particles emitted by radioactive materials. Rutherford expected the alpha particles to pass through the gold foil with little deflection, based on the prevailing plum pudding model. To his astonishment, some alpha particles bounced back at sharp angles, as if they had hit something dense and positively charged. From these observations, Rutherford proposed a radical new model of the atom. He concluded that the atom was mostly empty space, with a tiny, dense, positively charged nucleus at its center. The electrons, he suggested, orbited the nucleus at a distance, much like planets around the sun. This model, known as the Rutherford model or the nuclear model, revolutionized our view of the atom. It established the existence of the nucleus and introduced the concept of an atom with a vast amount of empty space. However, the Rutherford model had its limitations. It could not explain the stability of atoms or the specific wavelengths of light emitted by excited atoms. A new model incorporating the emerging field of quantum mechanics was needed to address these puzzles. Section 5. The Bohr model. Electrons in orbit. In 1913, Niels Bohr, a Danish physicist, addressed the limitations of the Rutherford model by incorporating the principles of quantum mechanics. Quantum mechanics, a revolutionary theory that emerged in the early 20th century, proposed that energy exists in discrete packets called quanta. Bohr proposed that electrons in an atom could only occupy specific energy levels or orbits around the nucleus. These orbits were quantized, meaning that electrons could only exist at specific distances from the nucleus, not in between. Bohr further postulated that electrons could jump between these energy levels by absorbing or emitting photons of light with specific energies corresponding to the energy difference between the levels. This explained the unique spectral lines observed when light from excited atoms was passed through a prism. The Bohr model, while a significant improvement over the Rutherford model, was still incomplete. It worked well for hydrogen, the simplest atom, but failed to accurately predict the behavior of more complex atoms. Despite its limitations, the Bohr model was a crucial stepping stone toward a more complete quantum mechanical description of the atom. It introduced the key concepts of quantized energy levels and the relationship between electron transitions and light emission. Section 6. Quantum mechanics, a paradigm shift. By the 1920s, it became clear that a radical new approach was needed to fully understand the atom. Classical physics, which had served so well in describing the macroscopic world, was inadequate to explain the strange and counterintuitive behavior of the subatomic realm. Quantum mechanics, a revolutionary theory developed by physicists like Werner Heisenberg, Erwin Schrödinger, and Max Born, provided the necessary framework. Quantum mechanics abandoned the deterministic view of classical physics, embracing probability and uncertainty. Instead of fixed orbits, electrons were now described by wave functions, mathematical functions that describe the probability of finding an electron in a particular region of space. The exact position and momentum of an electron could not be known simultaneously, a principle known as Heisenberg's uncertainty principle. This probabilistic view of the atom was a radical departure from classical physics. The atom was no longer a miniature solar system, but a cloud of probability, with electrons smeared out in space. Quantum mechanics provided a far more accurate and comprehensive description of the atom, explaining its stability, spectral lines, and chemical behavior in ways that classical physics could not. It laid the foundation for modern chemistry, materials, science, and electronics. Section 7. Beyond the atom particles from the void. While quantum mechanics revolutionized our understanding of the atom, it also revealed a universe far stranger than previously imagined. The quest to understand the fundamental building blocks of matter did not end with the atom. Physicists discovered a zoo of subatomic particles including protons, neutrons, quarks, and leptons. The standard model of particle physics, developed in the latter half of the 20th century, describes the fundamental forces of nature and the elementary particles that make up all matter. The atom, once thought to be indivisible, was now recognized as a composite structure built from even smaller and more fundamental constituents. The nucleus, once a tiny point at the center of the atom, was now a complex structure of quarks bound together by the strong force. The discovery of these subatomic particles and the development of the Standard Model marked a new frontier in our understanding of the universe. The atom, once the ultimate building block, was now a stepping stone to even deeper mysteries. Section 8. The atom today, from medical marvels to quantum computers. Today, our understanding of the atom continues to advance at a rapid pace. The atom, once a theoretical concept, is now a tool manipulated and harnessed for a wide range of applications. In medicine, radioactive isotopes are used for diagnosis and treatment, providing doctors with powerful tools to combat diseases like cancer. Medical imaging techniques, such as PET scans and MRI, rely on our knowledge of atomic structure and interactions. In materials science, our understanding of atomic bonding and crystal structures allows us to design new materials with tailored properties, from super-strong alloys to flexible electronics. Nanotechnology, the manipulation of matter at the atomic scale, holds the promise of revolutionizing fields from medicine to computing. Quantum computers, still in their infancy, exploit the strange rules of quantum mechanics to perform calculations that are impossible for classical computers. These machines have the potential to revolutionize fields such as drug discovery, materials science, and artificial intelligence. Section 9, Unraveling the Universe, the Atom's Enduring Legacy. From the philosophical musings of ancient Greek atomists to the mind-bending world of quantum mechanics, the journey to understand the atom has been one of the most profound intellectual adventures in human history. The atom, once a symbol of the ultimate indivisible unit, has revealed itself to be a gateway to a universe far richer and stranger than we could have imagined. Our understanding of the atom has not only revolutionized science, but has also profoundly impacted our lives, leading to technological advances that have reshaped our world. As we delve deeper into the subatomic realm, we continue to uncover new mysteries, pushing the boundaries of knowledge and challenging our understanding of the universe and our place within it. The atom, once a limit, is now a beginning, an invitation to explore the endless frontiers of the cosmos.